All right, welcome back. We have understood the theoretical aspects of mass capacitor by now. So in this video, I would like to briefly show you the use of Nanohub. There is a tool called MOSCAP or Nanohub, and it's very, very useful to analyze mass capacitors. So you could try various scenarios and then study it. So we will use the basic part of it today. In the next week, we will analyze CVs using the same tool. Okay? So to get started, so this is Nanohub. I already introduced to you for PN junctions. So log into Nanohub and then go to resources and find tools. Okay? And within the tools, you will find a tool by name MOSCAP, MOSCAP. So that should be right here. So MOSCAP, right? This is the one. So I'll go here. So this is a capacitance of a MOS device, it says. Okay. So now let us launch this tool. It's taking a little bit of time. Yeah. All right. So here we are. Okay. So this is the front end of the tool when it opens for you. And let me this should be good. Okay. So there are a lot of features in this. Okay. Before we get into that, so basically we could use, right now we will just use single gate. There's something called as double gate, which we will not study in this course essentially almost. Okay, and then the gate insulator thickness is 0.1 microns. We leave it at this. This means 100 nanometers of insulator. So this is the basic structure of the device. So you have the metal blue, insulator which is red, and the semiconductor which is in green. Okay, so the semiconductor doping is shown as 1 into 10 power 15 here. If you want, you could change it. For example, click it and then 16, 15, whatever. Right now we leave it as 15. All right. So gate oxide thickness is 100 nanometers, which is good. This is essentially telling you how many discrete points are there in the gate insulator. We leave it at 100. Gate insulator's dielectric constant is 3.9. So right now this is silicon dioxide dielectric constant as we have seen. In the next week we will see a little bit about how you can change this. And semiconductor thickness is 5 microns. Well, we could actually simulate for larger, because if you look at the actual wafer, I told you it is 500 micrometer thick. It is practically, it's not really necessary for us to simulate that long semiconductor because most of the essential physics is happening within the first few microns, right? So we will simulate for 5 microns, that should be sufficient. The number of nodes in the semiconductor are 200, which is okay. So P-type semiconductor, uniform doping, I could actually change the doping concentrations to some other, there are not, you could change, in principle, you could specify some functions. I don't know if this is allowing. So at least on my screen, it doesn't seem to be allowing any options. All right. So, and gate electrode, we will choose it to be aluminum for now. Okay. We changed this. Default was, I think, N plus poly, but we will talk about this next week. So for now, we will choose gate electrode to be aluminum. Okay. And then there are some parameters which are fixed oxide trap density and this, which you don't need to worry about right now. And then there is environment tab, which tells you what is the range of simulations. You can run it from some initial voltage to the final voltage. Okay. And then number of voltage steps is fine. Rest of the parameters are fine. We can leave it. And this too, you don't need to worry about. Okay. So that's it. So we made one change. We change the gate electrode to aluminum. Okay. And we hit simulate. Okay, let me do this so that it's clearer. Okay, so the result that shows up is what is known as CV characteristics. We will discuss this in next week. So right now I want you to go to, let's say, the other things. Okay. The CV characteristic we drop, so we can look at surface potential as a function of gate bias. You see, as you change the gate voltage, the surface potential is changing. This is exactly what we have discussed in the last lecture. Okay. So we said that it is surface potential from 0 to 5f will be in that expression that we derived, and after that it's going to not vary so much. So this sort of S-shaped curve we saw in the class as well. Okay. So energy band diagram. Okay. So this is at no Vg equal to 0. So no applied bias. Okay, this work function difference I have to talk about. It tells you that basically there's a Fermi energy here and there's already depletion of semiconductor because bands are bending downwards. So here there is certain doping density and then there is already some depletion happening. Okay, why it is, we have to actually, it's in advance, you will study it in the next week. Okay, so we could look at, let's say, electric field. Okay, at applied gate voltage of 0 volts. So in 0, actually it turns out it's already depleted. So we can look at the field here. Let me do this, zoom in here. So I actually click the x-axis and then moved it to actually zoom it out. Then I'll just zoom in this part, which is of interest to me. Okay, so what you see is the electric field is linear function in the depletion region, and there is a small region here. I think the interface is now 0. Okay, so this is the gate. Left of 0 is gate. So there is 1 micron thickness, and then there is this field difference here, and then there is linear change. So here the peak electric field is turning out to be about 12,741 volts per centimeter. And if you look at the field in the oxide, it turns out to be 38,000. So 12 times, you can compute 12 into 12,500. So 3 times will be 36, 37,500 or so. So 38, close to 38. Okay. So this is how we explain this jump, why this jump should come about because of boundary conditions, Gauss law, right? And you can also look at the hole density. So it's a p-type semiconductor. So the hole density was supposed to be 10 power 15, but it turns out that from 0 there is, okay, so 0 is here, 0.1 micron, right? The 0.1 micron is flat. So basically it is completely depleted here. And then the holes are increasing in this fashion, right? So we saw this. We defined a delta depletion this way. We made a square, right? Here, rectangle, sorry. But essentially, yeah. So minus 10 power 15 is what we were showing. So it's completely depleted, all right? And you can also look at electron density. Is there any electron density? Well, it turns out that it already is inverted at this point, okay? So I'll have to look at, slightly change this, okay? Let me go back. So since we are running at -3, final voltage, okay, this is electron density at last applied gate voltage, okay? At last up means I have applied 5 volts. So when I look at this is also a hole density at the last applied bias. So it's at 5 volts gate voltage, okay? It's fully depleted. And I look at electron density, it is having 10 power 15. This is 10 power 15. So this is the background doping, but we have electron density to be close to 10 power 18. So 3 orders of magnitude higher. So you see 1000 times higher electron density at the interface. And if you look at the net charge density, you'll see that this is the hole density part, which is what you would expect, holes are depleted. And this is the electron density part, okay? And this is a space charge. That's right, the net charge, right? This is removed and this is electrons have come in, so net charge total is this. So there's a huge accumulation here of electrons in the interface, okay? So in this fashion, you could study electrostatic potential. So, well, yeah, electric field at the last applied gate bias. This is interesting. So we are looking at, so this is your linear part of this curve, right? You should check this out, okay? So here it's the electric field is 0 in the bulk of the semiconductor. As you're going, there's a depletion region, so there's a linear change, something around 16,000 volts per centimeter. But then at interface, it is 52,000, okay? So you'll see that this is actually slightly higher than actually the ratio of epsilon silicon by epsilon oxide, okay? You should think about why that is so. So we showed this Gauss law was saying that epsilon oxide into electric field in the oxide should be equal to epsilon silicon into electric field in the silicon. That is true when you don't have any sheet charge. I mean, here the inversion charge itself acts like a boundary condition. So you have to account for the inversion charge also. Because of that, if you look at the electric field here, it is about 52. At the edge of the depletion region, it is 14, so 14 more than 3 times, right? It's getting to more than 3 times. So you can compute and check it up. So this difference is coming because if you look at the electron density in the same curve, again the same thing, but so electron density is very substantial. So how does the electrostatics work when you have such large electron density at the surface? Well, there has to be a discrete jump in the electric field. So one part of it is because of Gauss law, because of the dissimilarity in the dielectric constant, there should be a jump in the electric field. The other part of it is because of the sheet charge present at the interface, there should be a further jump. So that's why. If you look at this, unfortunately here you can't look at any particular voltage. So let me take -1, okay, where I know that I think this should be in depletion, or even 1.5. Okay, there I know that it will be in depletion mode. Unfortunately, if I can only see the last applied bias. So I was seeing only 5 volts. So now I'll run it only till -1.5. And if I do that, there's a lot of background calculations that go on. So this is something that you don't see, but yeah. All right. So it just started depleting. Let's see. How do I know that? Well, I can no gate bias. There's already some depletion. But if I look at the last applied voltage, let me look at the bands. Well, okay, no, I'm wrong. So at -0.5, you see I'm actually still accumulating. You see this? That's why this is interesting. You can correct yourself. See, I was thinking that it's going to be depletion, but it turns out that it's still an accumulation. So the EF is closer to EV, so it's accumulation actually. So let's see, it's an interesting thing. So now let's look at the whole electron density. See, there is excess hole density, so automatically the electron density has fallen here. But if you look at the hole density, you see, this is 10 power 15, which is the background. But the moment you come to the surface, you saw this sharp spike that I showed you in the exact solution, right? That was analytical calculation, but this is actually numerically, you can try to compute for different doping concentrations and check. This is background 10 power 15, so already hole density is about 10 power 16, 4 into 10 power 16, so 1 order of magnitude higher. If I want to see depletion, what should I do? I should choose a slightly smaller voltage. Maybe I'll say 0.5. I hope that it's still depleting there. So, well, you might wonder, how can depletion be there at -0.5? You told us that the gate voltage will be positive for depletion. The difference is coming because of metal. I will talk about it in the next lecture. Okay. We have so far discussed what is known as ideal mass capacitor, but the real case always there is a metal work function which is never going to be equal to the semiconductor work function. There's going to be a work function difference, because of which we have to consider something. We have to do some changes. We'll do that in the next week. Okay. Let's look at band diagram at the last applied voltage, energy band diagram here. Yeah, now we have depleted. We have just depleted it, right? So you should be comfortable doing all these things. So look at electric field then. Electric field at last applied voltage. Okay, so now we have electric field. Yes, this is a linear part. We have not really depleted much. That's why the depletion width is only going up to 0.6 maybe, or 0.7. And look at this number. This is 7,800. And this is 23,000. 7,800. So 7,000, 3 times should be about 2,100. 2,100. Sorry, 21,000. And then 800 into 3 times should be equal to roughly 2,400. So yeah, 21 plus 2,000, 23,400, 22,550 it is showing you. Okay, it's very close to the exact number what we like. But in the last previous simulation where you had, simulation 2, I think it was, you can go back or you can plot all of it. You see here, yeah. So this was, I think, one of the simulations where electric field, the first one was already depleted. And the second one, I think, where we had inversion. Yeah, you see this. This is wonderful. When you have inversion, there's a much, much bigger jump. Each of these things you could export and check the data. So there is a much bigger jump here. So yeah, it's here. And then from here to here, you have to check. And from this to this. So essentially, whenever you have inversion charge, there's an additional jump in the electric field. Okay. So that is one. If you look at the potential, electrostatic potential, well, yeah, this is surface potential, I called it, right? In the semiconductor, there is a surface potential and then there's a linear function, isn't it? So you see this. This is fantastic. You see the quadratic potential, and then there's a linear variation in the oxide. But this is at high inversion, and we already inverted this in the simulation case. This is for the simulation 2. One of this was actually depleting. So this is one depletion. Right now, currently we are depleting, simulation 3. And this is low amount of inversion. Okay. So for various situations, you'll see surface potentials. You can calculate everything that we have discussed in the class. The same, you can look at surface potential as a function of wave gas. So we have run different simulations. Okay. So now, if you want to, essentially in the next week, we'll see how to design these things. Okay. So far, you're only learning the physics, but when you're using MOSFETs, we'll have to design them. How to design them, we'll see that in the next week. Okay. So this will be the first step in designing a MOSFET. Let's go back now. I cleared all the simulations. Let's try to look at an N-type semiconductor doping. Okay. If I do that, I just kept aluminum again. Let's see what we get. Okay, so now we have started to invert. Okay, so let's look at, let's change it a little. I want to go up only to -1. I don't want to do till -3. I'll explain later why it is. So I'll clear this simulation. I want to run it one more time. Right. So let's look at fast applied bias is, I guess, 0.5. Let's hope that it is so. Okay. Charge density now is this positive number, hole density. Okay, there is a large hole, 10 power 5 or so. This is not so much actually. This was an N-type substrate, N-type, and you're having less. But then let's look at the net charge that will have everything. So this is your hole, but then electron. So this is electron concentration, which is very, very steeply falling. Let's look at electron doesn't get lost in bias. Yeah, N-type semiconductor we have depleted, but not a lot actually. There is a very, very small depletion. Okay. So how does a band? The easiest way to identify what mode we are running on is basically looking at band diagram. So you see here, okay, this is N-type semiconductor. So this distance should give you the doping density of 10 power 15. And then we have slightly depleted it. We have not really applied a gate voltage enough to invert it. Okay, so if you want to invert it, we'll have to go to large negative voltages. That's fine. Instead of this, I'll go to -3 here, just for, let's check it out. Let's see if it inverts at that time. So PMOS has to go to negative voltages to invert, whereas NMOS will go to positive voltages. There's a small correction term that will come about. I'll leave you to analyze what happens. Well, I don't think we have managed to. We have inverted -2 or -3. Okay, let's see. Energy band diagram at last applied gate voltage. Well, yeah, so N type, but now this has come this has come relatively close, right? Definitely closer than this distance. EF and EI, EF and EC, this much distance, right? So it's definitely closer. So basically we have more holes than there are electrons in the substrate. Let's verify that. So hole density, is 10 power something, 10 power 17, whereas electron density would be 10 power 15. That's the substrate. Actually, in fact, we have removed electrons from we have pushed away the electrons and we have created a space charge, and then we have created a inversion layer of holes. So if you look at this, you should combine this. This is the electron density. So electrons are not present in the closed, this is the depletion region. And then the net charge, hole density is this, only at the interface you have holes. The total density would be basically holes, electrons, and then this is also including the space charge. That's why there's a flat here, and then it's coming down. Okay, the total is coming down. So what else can we do? We can look at electrostatic potential. Interesting. See, I showed you that there should be a minus. The linear electric field should be like this, right? Decreasing function, like this linear here, and then there's a sharp change here. So sorry, yeah, electric field should be linear, yes. And then in the oxide it should be constant. Let's check it out. Well, it's too close here. We are not able to distinguish. It's too close. Electrostatic potential. Okay, so let's go back and try to. Okay, we need to do it at normal voltages because we have inverted. There's some, because of the charge, there is some strong changes here. So we should actually be in depletion. So if you want to be in depletion, I would say let us just do the previous simulation. Let's see. Previous simulation. Well, we are not reaching also. I mean, there's a gate voltage that should be linear here. So this till here it is quadratic, and then it is linear. So this is how the voltage will be. So this is applied voltage of about, I would say, if I take this to be 0. 0. Oh, okay. The reference is taking here simulator slightly differently. 0.3 as a reference. So with respect to that, we have 0.14. Okay. So there is this gate potential, electrostatic potential that you will see. So well, I mean, you see, this will be similar again. So there are a whole lot of things you can study based on this energy band diagram without any applied gate voltage. There is an accumulation now. See, this is interesting. In the last case, we saw depletion, but in case of aluminum, we are seeing accumulation. So we will explain this in the next class. Okay. So you can play around with many things here. It's just your interest and how much you want to check. Okay. So as a small take-home assignment, or you just can do it or don't do it, up to you. But I would encourage you to think about what are the various ways of changing VT. Just change some parameters and try to see if VT will change. That means the point at which inversion happens changes. Okay. What are the various parameters that we can tweak? Because I said VT is one of the most important parameter when it comes to design of semiconductor devices. So what are the ways to control VT? Increase, decrease. Play around. Let's say what happens if you change the oxide thickness, right? Or if you change the permittivity, what happens? Each of these parameters you could it won't help if you change the thickness of semiconductor much, but definitely if you change the gate, it will change, right? So you see some of these things and see if you can analyze, okay? So you'll have a lot of questions, I'm sure. You will not be able to understand a lot of it, but it is good to have those questions. So as I keep saying, the best way to learn is to explore, look at what doesn't make sense, ask questions about why it doesn't make sense, analyze, then that is how you will learn deeply. Okay. So that's why I like these sort of software tools, which will help you play around. If you have to do it by calculations, it will be very tiresome. All you have to do is simply click. I know this interface is not the best interface, I think, but I think it does a really wonderful job in capturing the essential physics. Okay. So please take some time and analyze these things. We will give you a few problems in the assignment, which will make you run this once and then extract some numbers and then just put it in the assignment. Okay. All right. Thank you so much. I'll see you in the next week. Have a great week and thank you.